So make sure that that happens, and then in the middle, this will define your columns. So this is the first column, this is the second column, and then you see this little line thing that actually tells you that you're going to have a line, a vertical line. So this is going to be, this first cell is 2.5 centimeters wide, and this next one, so this next column is 10 centimeters wide. So in other words, you'll have something that looks like this, and then there's going to be an invisible break. And then it's going to go all the way to like there or something. So essentially, what you're going to have here is, I'm just going to draw out what this is going to look like, and then, yeah, so this is essentially going to look like pretty much like that. So notice that I don't have a line over here. If I did have a line there, we would have this. But we don't, so there is not. And yeah, it's just, that's all that is. It's not that difficult. I feel like people keep overcomplicating this. Either that or very oversimplifying it. So make sure that it's just, you have these things here. This means you have two columns. That's it. And then you just define how wide those columns are. If you did C and C, that just means you have two centered columns, which would make it so that this is center and this is center, and yeah, that's pretty much it. So let's look at an example that might help you for the homework. So again, tabular, begin tabular, and then you have these two braces. I'm just gonna color code them so that we know these are the start and end ones. Always draw those first, or write those first no matter what. I just noticed that the thing got a bit off-centered. I'm not sure how, but it did. So start and end ones, and then there's the column, there's another column, and so we just have 1, 2, 3, 4, 5, 6, 7, 8 columns here essentially, and each of them alternate between 0.2 centimeters and 3.5 centimeters. So why in the world would we ever want to do that? Well, when you're writing problems, that might be actually useful. So if you want one column over here for the number that's like 0.2 centimeters, then you can do that. And then the next thing, this is going to be 3.5 centimeters. And if you look at this, we have the and symbols. Remember, and symbol means column break. So literally, the column itself will break. So it means this is the end of. So this is the end of that. And then this one is the end of that, and so on. So in LaTeX, it doesn't actually matter too much if you just do enter like once within here. Don't do it 2 times. That actually means that you're going to break the code, and yeah, just don't do that. So just, you can organize it like that so that you can see, okay, 0.2, 3.5, 0.2, 3.5, and so on. So what does that actually look like in the end? This. So essentially we have 8 columns. We have 1, 2, 3, 4, 5, 6, 7, 8. And then we've made that. This is very similar to what I'm expecting you to do in your homework. So yeah, remember to turn this in before the test. Send it to me. Don't be the person that decides, oh, maybe it doesn't actually matter. No, do it. Also, be aware, remember, caret symbol, braces, exponent that has more than one character. If you have just one character, you can do caret symbol that character. But here we have -1. That's 2 characters, right? And then \frac, I just want to highlight. Numerator, denominator. And then in the numerator, there's another set of braces, so just be aware of where the braces are and what they cover. Literally, one of the reasons why I'm teaching you guys how to use this program is because it'll force you to understand that concept of where to put parentheses and groupings and stuff like that. Okay, so fractions review. Let's review this stuff. And yes, I just want to re-emphasize. Fractions should be easy by now. I know that they're annoying. They're annoying to me also sometimes. But they're not necessarily difficult to do. So, just, yeah, do that. It's easy to start working with them, just like go through the basics. So, addition and subtraction, get a common denominator. Multiplication, directly multiply across. Division, top times reciprocal of the bottom. Do not ever say division means reciprocal. Well, yes, reciprocal of what? So you need to give context to that. So let's look at this. And yes, this is a division problem. So you have a fraction over a fraction. So the top of it is pi/2, right? And then the bottom, you just take the reciprocal of 1/5, which is 5/1. So we end up with 5pi/2. Okay, so then we can look at that bottom one. I'm gonna write that bigger just to make it easier to see. So that's x+1. Yeah, I thought that was a lot bigger than it actually is. x+1 divided by xy, all divided by 1/x minus 1/y. Okay, so at first you might be like, oh no, what do we do here? Or, oh, PEMDAS. No, PEMDAS does not work. Essentially what you want to do is, so you know that you need to multiply by the reciprocal of the bottom. How do you get the reciprocal of this? If you ended up with x/1 minus y/1, that's called wrong. Because that's not the reciprocal of the bottom. That's the reciprocal of each part of the bottom. But unfortunately, that's not the actual reciprocal. So what should we do first? Combine these so we have one fraction. So we do nothing to the top because we just do top times the reciprocal of the bottom, right? So, oh, sorry, I didn't mean to do the times there yet. And then let's just do this. Alright, so in order to get the common denominator, in this case, you would just have to multiply by the other thing. So you get y minus x all over xy equals, now we can have top, bottom reciprocals. x+1 over xy times xy over y minus x. Okay, so nice things happen here. The xy and the xy will divide out, and then we end up with x+1 over y minus x. And that is it. So, again, not too difficult of a concept. Just make sure that you're able and willing to, well, practice and understand it. Okay. Now let's go over function composition. Oh, by the way, if you want practice with this, just look up, what is it? Simplifying. I'm not sure why Photoshop is lagging. So just look up simplifying rational expressions. Simplifying rational expressions. Okay, function composition. Let's go over this one. This is one that was strange. One that people were not getting as easily as I would have hoped. Again, don't overcomplicate it, otherwise it's going to be difficult. So let's just look at this part for now. So, if f and g are functions, then this f of g of x is how it's read. It's function composition. That basically just means here g is going to become the actual input for f of x. So the x in f of x becomes g of x. So it'll be very, very obvious in this example right here. So if we wanted to find f of g of x, that would be, here's f of x in yellow, here is g of x in blue. So f of g of x equals the square root of 3 times, and it's like literally just multiplied by g of x. There's nothing fancy about it. Minus 3. I'm just going to erase that. So there's space. Okay, so that's going to be 3 times what in the world is that thing. So just directly substitute that thing in. And do not overcomplicate this. Again, overcomplicating is going to make it a lot harder than it needs to be. If you don't overcomplicate, you'll be fine. Okay, so a 3 is going to divide with this, and I'm going to multiply there. So we get x squared plus 3 minus 3. That's going to subtract out. And then we end up with this. So nice thing is we actually end up with x in the end. So yeah, that's a thing. And let's see. So that was a nice result. So what if we did it the other way though? What happens if we do g of f of x? Okay, so let's literally just do that same thing. So we have 1/3, and then that thing's going to be squared plus 1. That thing is f of x, right? I'm just going to write f of x again for emphasis. So again, this is not difficult unless you overcomplicate it. Or if you just look at it and go like, oh my goodness, this looks hard. Okay, so let's see. That's going to be the square root of 3x minus 3. And then everything else the same. By the way, you don't have to color code this. I'm just doing this for emphasis. Alright, so square root and squared, they'll divide out, or not divide out, they'll just cancel out. 3x minus 3 plus 1. Okay, so this 1/3 is going to multiply to all of these. That's going to divide out with the 3. X minus 1 plus 1 equals, those subtract out, we end up with x. So this is an interesting thing that just happened. we had f of g of x, and the result was x. We had g of f of x, and the result was also x. So that's a nice little pattern. What happened there? Spoiler alert, that's a special thing. By definition, two functions f and g are called inverses if what just happened actually happens. And here's the reason why, again, just because I need to review it again. We've gone over this a few times, so make sure that this makes sense to you. Okay. So an example of that, you can see the previous problem. You can also look at your review packet from last time and just look up checking inverses. If you look up that, you will find a bunch of problems that help you practice that. And okay, so let's practice another thing though. Okay, so that's supposed to be a small 3. It's just a little bit too small. I didn't realize how small it was going to be. Okay, so find the inverse function. So you might look at this, be overwhelmed, to be like, oh my goodness, what is this? So let's just do it slowly, part by part, make sure that it makes sense. Okay, so this is your y value. So how we do this generally is just switch x and y. And then literally solve for y. So that'll be x equals, this is the cube root of 3y squared minus 4. How do we get rid of a cube root? You literally just cube it. X cubed equals 3y squared minus 4. Then let's see, what's the next most logical thing to do? It is not getting rid of the 3. You want to add 4. So when you add 4, so the reason why you don't want to do that is because 4 is not a factor of 3. So if you divide 3, you have to divide it from the 4 also. Okay, now we can divide the 3 because there's only that 3. And we'll get x cubed plus 4 divided by 3 equals y squared. Now we can square root that. And then we get y equals x cubed plus 4 over 3, but their square root, because that's how we got rid of the square. And if you want to write this properly, you can also write that as, because the original was f of x, you have f inverse equals this. By the way, don't call this f negative 1, call it f inverse, because that's correct. Okay, so here's a thing now called set notation. So we're gonna learn about a few things called sets. You probably haven't gone over them directly a lot during previous math classes, because it's not exactly super common to talk about them super in depth. So we're gonna do that here. So when you started learning about math, just numbers in general, you probably started to learn 1, 2, 3, and so on, right? So this is just a natural counting sequence, right? Whenever you learn how to speak a new language, chances are counting is one of the first things. So learning English, 1, 2, 3, 4, 5. If you learn Spanish, 1, 2, 3, 4, 5. Greek, 1, 2, 3, 4, 5. Mandarin, 1, 2, 3, 4, 5. Japanese, yeah, you get the point. 1, 2, 3, 4, 5. Anyway, so the point is you count. So there's this symbol, It's an n with a slash through it. So these are called the natural numbers. Alright, cool. So we have these. Well, these are not the only numbers that exist, right? They're obviously the most like used just in certain contexts. But we can also do other things. So sorry, I meant to do that more over here. You'd extend this, right? So what if you had a 0 and then went backwards? -1, -2, -3, and so on. Because it's just the exact same thing, but the other direction, right? So this is another special set. These are called the integers. Integers just means whole numbers. And a whole number can be positive, it can be negative. It could be technically 0. So we have this new set of numbers. By the way, I'm doing this so that when I mention these sets, it makes sense. And also, in college, professors will pretty much assume that you understand what integer, the difference between integer, natural number, rational number, and stuff like that. So what if I got an integer and another integer and divided them by each other? So, for example, if you had something like 1 and you had something like 2 and they were divided, that's a fraction, right? So let's say, again, I'll do this down here. It'll make more sense later. So let's get an integer, let's call that p, and get another integer, let's call it q, and they're divided. And they are, again, I'll explain this notation again. We've gone over it in class, but yes. So some integer p and q. So what is this? Well, this actually also has a special name. It is a q. So this thing is called the rational numbers. I have no idea why it's a q. So these are called the rational numbers. In other words, everything that's a fraction. So you see this word ratio or rations whenever you hear about like wartime rations or like finding ratios, it's always a fraction, right? So I'm just going to draw a box around all of this because technically all of them are rational numbers. So like for example, like even 2, that's just 2 over 1, right? Okay, well, how about this now? What if we had other numbers? Numbers that were not an integer over an integer. Something like the square root of 2. Or pi. Those are not able to be written as fractions. Therefore, this actually is not this is not part of the rational numbers. It's a completely different set on its own. So this actually is called, instead of rational, it's called the irrational. So this does not mean, so I know that the word rational also means like logical in a way. This does not mean that. This means something completely different. This just means not in a ratio of some sort. So there's an infinite number of these also, so I'm just going to put dot dot dots. And the symbol for this, you don't necessarily use it a lot, but it's q with an exponent of c. So that c means complement. Complement just means not, essentially. So notice that with this one, I'm drawing the box a little bit different. I'm not going to be drawing it around Q, but rather as an extension to it. Alright, well, last thing then is, what if we just looked at all of these as numbers? So literally any number that's rational or irrational. So notice that the rational numbers included the integers and the natural numbers. The irrationals were just not that. So the thing about saying not something is you have to say not something out of what? Like if you said, I want all of the even numbers from 1 through 10, you can just say the non-odds between 1 and 10. Because if you just say non-odds, that could just mean any even. But if we look like this, then we have a set that you have to be saying exclude the stuff that's not rational from this set. And that one is actually called the real numbers. So that is this symbol, R with a slash through it. And it is a set where you take the rational numbers, and then you see this U thing, that means union. That just means you put something together. You take the rationals and the non-rationals, you put them together in one, and that becomes the real numbers. So when you hear people talk about something called the real numbers, that's what that refers to. It doesn't necessarily mean like some numbers are fake. So here is what we get, the real numbers. Okay, so just want to give you that terminology so that you understand that when you hear it, because you will hear it either from me or from someone else in the future. Alright, so I also wanted to just quickly talk about this thing. There's a notation we're going to use for domain and range and stuff like that. So this is just quick review. You can just take a picture of it real quick, because I'm just going to move on. Alright, so here's the unit circle. We have seen this many, many times. You should know the unit circle. You should be able to find all of the patterns in it. It is not super difficult to do. So let's talk about those patterns. So patterns in the unit circle. To get all except for the pi over 4s, all you have to do is add pi over 6 to the previous angle. I don't know how that got cut out. I'm going to redraw that in there. Close enough. That looks like a pi, right? I mean, what else is that going to be? But yeah, so here's a unit circle. Look, there's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6, or 0. So that's gone. And just, yeah. You can look at it like that. Certain things divide out. Cool. And just simplify. Alright, so then for the rest of them, all these red ones, you literally just add pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6, 7, 8 pi over 4. That was a terrible 8. And that was with my dominant hand. Yeah. So that is that. So make sure that you understand that pattern. That is going to be useful for literally everything. Alright, so next, let's talk about the coordinates. Pi over 6s, pi over 3s, and pi over 4s. They all have the same coordinates relative to each other. Make sure you understand that. Make sure you're willing to understand that. So the pi over 6s have square root 3 over 2, comma 1/2. Pi over 3s have that switched. Pi over 4s have 1 over square root of 2 for both coordinates. The only thing that changes is positive or negative depending on, again, the quadrant. Make sure that makes sense. This will help you immensely when you are doing things with the unit circle. Pretty much anything trig, actually. And then just a quick reminder here, when we're evaluating trig functions, we can use that. Oh, also, yeah, that thing. Sine over cosine, that's another way to define tangent. So y value, x value, y over x, so sine over cosine. Again, just take a picture of this if you need to remember it real quick. So let's go over some concepts and how to evaluate these. And again, these things should be things that you're able to do like fairly quickly. So, trig function means that you take in an angle and output a ratio in a triangle. And then inverse trig just does the opposite. You get the value and you try to output the angle itself. So I'll give us a minute or two to kind of look at these ones, try to figure that out. But before we do that, let's look at this real quick. So we can only choose certain angles for the inverses. For sine inverse, remember that's going to be negative pi over 2 to pi over 2. We went over this, and then for cosine is 0 to pi, and tangent inverse is negative pi over 2 to pi over 2, non-inclusive. So make sure that you have that like that. Make sure that you don't have the equal to parts under there. So try to find these through that. I'll give us a few minutes to work on that. Alright, so let's go over these. Okay, so sine at negative pi over 2. So if you imagine a unit circle, that means you're going from 0 and then 3 pi over 2 this way, which is going to be over there. This is going to be negative, and then sine at the pi over 3's is going to be square root of 3 over 2. Okay. And then so cosine of 3 pi over 2. So going in the positive direction, 3 pi over 2 goes over here. Cosine is going to be negative 1. Wait. It's the x value, so it's going to be 0 there. Cosine is 0 at the pi over 2's. Alright, and then the last one for this, tangent of negative 4 pi over 3. So we start here, we go... So 4 pi over 3 is a little bit more than pi, just one more over, so that's there. You don't need to be exact, you just need to know where it is. And then tangent is going to be negative there, because it's going to be sine over cosine. Cosine's negative, so... And then it'll be negative square root of 3. Alright, cool. Alright, so sine of square root of 3 over 2. So, the question is, what angle makes sine equal square root of 3 over 2? So, we can make it so that, let's see. That's going to be at pi over 3. Because that's going to be the pi over 3 that's within this. Alright, and cosine equals negative square root of 3 over 2. There's a few of them, but remember it's going to be the one that's within this. So that's going to be one of the pi over 6's. Which one is it? It's going to be this one. It technically is there too, but we need to go between 0 and pi. So there's going to be 5 pi over 6. Alright, where is tangent square root of 3? So that's going to be at one of the pi over 3's. And since tangent goes between pi over 2 and negative pi over 2 and pi over 2, it's going to be at the positive one, which is there. So it'll be pi over 3. If it were negative, we just go negative pi over 3. Alright. So any questions on that so far? Make sure that you just be posting questions into the chat. I see one person on. I don't know if that's me? Or if there's someone else on also. Oh, there's 2 now. Cool. Anyway, I don't see any questions, so I'm gonna move on to this. Okay, so here are the 6 parent functions that you should know. Oh, whoops, something got deleted there. That's gonna be 1, that's gonna be negative 1, that's gonna be... pi over 2, and negative pi over 2. So I just drew this here. You don't necessarily need to draw it again right now, but I wouldn't say it's a bad idea to draw it. But yeah, so we have those. Now, I just want to go over some conceptual stuff before we go too much into this, because there's a lot to, I guess, just like think about, and a lot that you can process through with this, and a lot of logic. So logic is good. Let's try to logic through as many things as we can. Okay. So where is sine 0? So sine is 0 let's look at the sine graph itself actually. So I'm just gonna bring it down here. So sine, let's just grab that thing, and I'm gonna copy it down here. Cool. Interesting. Oh, the layer above it has stuff on it. Okay, that's right. Delete. I guess I should delete those here too, just in case. Okay, anyway, so if you look at that, we see certain points where sine is 0. And then here's where set notation is going to come in. Yay. Okay, so if we look at this, we have a few points. We have that. I'm going to use another color for contrast. This, and this. So that seems to be at all of a certain type of number. So if we take a look at what that is, that's at 2 pi, negative pi, 0, pi, and 2 pi. So that's at pi plus just like all the times a positive number or a negative whole number, just any whole number, right? So sine of 0 when theta equals a whole number pi. So let's just call it k pi, where k is an integer. So I guess technically what we can say is this is the solution set. So just using that set notation from before. Okay, so now what about cosine? Oh, whoops, that's on a different layer. Okay, so for cosine now, let's grab the cosine graph and move that on down. Nope, I mean to copy that. Okay, so let's analyze where this is doing that. We have that here, 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 here. So let's just look at the base one. That's pi over 2. Then we go to another one of the tick marks in between pi and 2 pi. So that'll actually be 3 pi over 2. And then that's going to be pi over, so that's 5 pi over 2. And notice it's actually going to be the same exact values in the negative direction. So what I want you to do is kind of think about that. Think about what is going to be that value. So the goal of this is just think. Try to think of how can you write this? What pattern do you see between all of those? So I'm going to give you like a minute or so just to do that, just because I do want us to practice that skill. That's a skill that'll come a lot in handy. Alright, so let's talk a bit about the patterns that you could have seen. The main one is probably, notice that's pi over 2, 3 pi over 2, 5 pi over 2. The next one you probably would have guessed is 7 pi over 2, 9 pi over 2, 11 pi over 2. So odd number times pi over 2. So the solution here could be all theta such that theta equals, I guess I technically should have put theta equals there, but yeah. So you can say 2k plus 1 or minus 1 times pi over 2, where k is in the set of integers. Alright. So where's tangent equal to 0? So that's going to be an interesting question. So something that I want you to think about is that tangent is sine over cosine. And we're going to use that idea rather than the tangent graph. So tangent of theta technically equals sine theta over cosine theta. So think, what would tell you that something is 0? So remember, just gonna give you a quick thing. A over b means how many times do you have to add b to get a? So one of them is gonna be 0 if you want 0. One of them is gonna be 0 if you want undefined. So try to recall which one is which. If you want to, you can answer 3 and 4 right now. Just think about that. Alright, so let's look at this now. So, what is it? So if the numerator is 0, then you get something that is 0, because then the question is, how many of the bottom do you add to get the top? You just don't add it 0 times. So that's going to be, this is where sine of theta equals 0. In other words, which thetas are those? Literally this. And then how about where tangent is undefined? That's going to be where the bottom is 0, right? And what is the bottom? Lo and behold, it is the other function. This is where cosine of theta equals 0. In other words, if I were to copy this, it is that. So how are sine and cosines zeros? So 0 just means where they equal 0 or their x-intercepts. Relate to tangent. Well, you can see that the zeros of sine are the zeros of tangent. And the zeros of cosine are the vertical asymptotes. so vertical asymptotes. So this is a helpful thing to understand, to be able to think about, be willing to think about. That's probably the bigger thing. So yeah, this is trig inverse, and some of the conceptual stuff. Now the rest of the time I do want to spend a bit on graphing, and then if there's time left, I'll go over another problem that I just kind of made up a little bit. So let's practice how to graph these things. Okay, so yeah, we have to figure out, first of all, what is the parent graph here? Because once we figure out the parent graph, that helps us understand the like starting point, so that we can actually start there, work on it, and get some good stuff going on. Okay, so what's this thing? We have cosine, or tangent, right? Cosine inverse is the next one, and I just saw that. That's why I said cosine. So let's figure out A, B, H, and K values. So A is a half, B is also a half, H is negative pi, actually. Because remember, this is going to be theta minus H. If this is positive, that means H was negative. Okay, so what else is helpful? Let's figure out the reference points. So, for tangent, you should be able to pretty easily, if you know the shape, this is easy to get. This is easy to remember if you know the shape. If you don't know the shape, learn it, I guess. Because it's going to be extremely important to be able to know what the shape of something is just by seeing the name of the function. Okay, and then it's helpful to list the transformations. That way you kind of have an idea of like what you're actually even doing in the first place. Okay, so we have A equals 1/2, so that's a vertical scale. Technically scaling, but yeah. But conjugations. Vertical scaling by 1/2. And then B is a horizontal scaling by 1/2 as well. So remember, this, for horizontal, you're going to divide all the x values by 1/2. Rather than vertical, you multiply all the y's by 1/2. Just look at that table that I gave you. Okay, so H, that's going to be a horizontal shift by negative pi. In other words, pi left. And then K, that'll be a vertical shift Okay, so there was a question on how I got pi over 4. So the parent graph looks like, I'm just going to draw it real quick here. So let's just say that's pi over 4, that's pi over 2. So this is pi over 4. I'll just write negative pi over 4 here too. So the asymptotes are going to occur at the pi over 2's. And then halfway between is where this happens. Let's see, I think that 1, -1, sure. And then you get this. Or this is what tangent looks like. If you don't remember it, make sure that you're going over it, remembering, just literally memorize every single graph. But yeah, so that's where that comes from. You can also remember unit circle. At the pi/4s, tangent, so the x and y values are both 1/√2. And if you divide them for tangent, you get something over itself, which is just 1. So that's another way you can remember that. Okay, does that help with the question? I'm just gonna get rid of that for now so that I can do the other thing. So I'm gonna write down scaled points and shifted points. If the problem still persists, let me know. Oh, I forgot to also write vertical asymptotes. Okay, so I'm just going to do the same thing down here real quick, just so that it's quicker to just, yeah. By the way, whoever asked the question, can you leave your name in the chat? Because I have no idea who that is. You might get something if you leave your name in the chat, like it said in the beginning. I don't know if you were here earlier, but anyway. Okay, scaled points, so we're going to multiply all the y values by 1/2. So -1 times 1/2 is -1/2. 0 times 1/2 is 0. And 1 times 1/2 is 1/2. And then divide by b. So that's going to be -pi/4 divided by 1/2. That's the same thing as multiplying by 2. Then we get this. And then for the h, we're just going to subtract h from all the x values. So here's the x value. Subtract pi. So if you do that, you'll end up with -3pi/2, -pi, and -pi/2. And then subtract 2 to all those. So if you've been doing just like working with fractions long enough, all those will be very easy to get. Yeah. So I'm just going to start drawing the axis real quick. Why does it keep doing that? Let's see. Maybe I want to do this. These are from the review, by the way. I'm just trying to remember. There was one of them where I had to have a lot over here. Okay, then I'm going to draw the asymptotes real quick. -% negative. Oh, I forgot to do that. Don't forget your asymptotes. So here, originally, that is, what is it? That's pi over 2 negative pi over 2, so multiply that by 2, we get negative pi and pi. If we subtract pi from them, we get negative 2 pi and 0. Okay, so now I can draw the asymptotes, and then I'll get the y-axis after that. Oh, that was interesting. We get that. Okay, cool. Okay. So now let's get some points going. We have, okay, so now we need to go by, we need to have like halves and stuff over. So let's just, oh, that's supposed to be white. I forgot to change the color. I'm gonna make that thicker. I'm just gonna go by, okay, so 1 through, why is this so thin? 1 through 5, that is definitely strange. Okay, there it is. The vertical asymptotes, the originals were these. It's just tangent is undefined at pi over 2, like all of the pi over 2's. And then you just transform, the same way that we transform these points is the same way that you transform the asymptotes. Literally exact same thing. Oh, I made a mistake on there. I don't know why I put y equals. Those are all supposed to be x equals. Okay, so 1 through 5. Negative 1 to negative 5. Okay, so anyway. So that'll be theta axis, y axis. Cool. So let's just plot those points real quick so that we can work with this. So that'll be negative 3 pi over 2, comma negative 5 over 2, so that's 2.5. Negative pi, comma negative 2. And negative pi over 2, comma negative 3 over 2, which is that. And then we end up with something along the lines of this. It kind of looks a bit nicer with the red over it, so that it looks like, look, there are dots emphasized. Okay, so I'm going to leave this for a little bit. If there are any questions, let me know. And then later on, I'm going to have you try the next one, and then I'm just going to show the answer at 4:45 exactly. Alright, so just in the interest of time, I'm going to go over, just start us on the next one. This is the problem. -1/2 cosine inverse of -2 times x minus 1, all plus pi over 2. Okay, so right now I'm going to just turn off the stuff that you can see real quick, and then I'm gonna do the thing, and then I'm gonna show it when I'm done, and then you can check it. Then that's essentially gonna be the end of the stream itself. All right, turning off in 3, 2, 1. Interesting. When I turn that off, the lag also turns off, kind of. Strange. Alright, so I've currently finished. I'm just going to project it here, so that whenever anyone who's watching has a chance and wants to check, you can check it. Obviously, it works better for you to not look up until you are done. So I'm just going to leave this here for a few minutes. If you're watching this after the stream is over, so watching the recorded one, then just check it. Pause it until you need to. So I'll leave it here. If you have any questions, let me know. But at 4:45, I'll just end the stream itself. It's still probably gonna go on a little bit after I technically end it. So yeah, just take a picture before 4:45 if you still need it, or just watch the video that's gonna be uploaded immediately right after. Wait, why are there like 5 people now? Interesting, I'm not sure why this thing is not displaying right now. Because I'm checking out the Twitch channel and I don't... Or maybe my internet's just lagging. Oh, I think my Google Chrome is lagging. Oops. Yeah, that's about to crash. Sorry, if you've said anything in the chat ever since I turned on the thing until now, I probably didn't see it because I didn't realize that my Chrome was lagging. So if you said anything, please type it again. I just got back onto the chat. So any comment that was after, where did I get the VAs? Around 47-ish, I'm probably just gonna cut it off, and yeah. So if you do have any questions, make sure that you ask before that. Alright, so about to end this pretty soon. Doesn't look like there are really any questions so far. The only thing that might be kind of weird is how do I get the curve to be the way that it's supposed to be? So it says reflection over x-axis and then reflection over y-axis. If you just you can literally just draw this out. You can do that with your own like graph or something, and then you'll see it happen. Like you can actually make a physical graph, flip it, and then you'll see how that's going to go. And I think I did it correctly. If I didn't, let me know. But I think it should be that. Alright, so about to end this. Thank you for watching for those over here. And if you need to watch the thing when it's uploaded to Twitch, you can do that. I'm probably going to put it on YouTube as well. Alright, thank you everyone. See you all on whenever the next time I see you is. Study hard, good luck. Email me if you have any questions. Bye.